Hello everyone, welcome to what will be pre-lecture number 14. This should be a really quick one. We're just going to talk about different kinds of acids and bases that we haven't quite seen yet. So first type that I want to cover that we have not discussed in class yet are something called polyprotic acids. And so a polyprotic acid, you may be able to guess from the name, is something that is able to act as an acid multiple times. So if we think about it, in our Bronsted-Lowry definition of acids and bases, if we start with 2 protons, we can react with water once, transfer one of our protons to our water to form hydronium, and we still have this 1 proton here. So this is our first conjugate base, and then that conjugate base can also react again with water to form a second conjugate base, this generalized A2-, and another equivalent of hydronium. And so we would call this polyprotic, where we have then 2 Ka values. And so we have Ka1 for our first dissociation and Ka2 for our second. And typically with all of these, basically as you go down, or up in number, I guess, for your Kas, your first dissociation is going to be much stronger than your second, and so on. The exceptions, or basically for our concerns with this, we only need to consider our first dissociation to determine the amount of hydronium in our solution. And that is, of course, what it will be affecting our pH. And in class, we'll go through an example of why that might be. Okay? There are some exceptions to this rule. So the 2 exceptions we have are when Ka1 and Ka2 are within 2 orders of magnitude of each other. So that would be, for example, if we have like 10 to the -2nd and 10 to the -3rd, that is within 1 order of magnitude of each other. So we could no longer make the simplifying assumption that we only need to determine the hydronium produced for Ka1. The other exception is when our acid concentration is within 2 orders of magnitude of Ka2. And so an example of this would be, say Ka2 is something like 1 times 10 to the -8th. If the concentration of our acid is something like 5 times 10 to the -7th, that is again within 1 order of magnitude. So it would be a very, very dilute acid at this point, and so this assumption can also break down when our acids are very dilute. Okay, so those are polyprotic acids. I also want to talk about how metal ions affect the pH of water. And so say we have a metal ion, and that metal ion has a charge of 3+, because we know water is going to have a neutral charge, right? So even if we have 6 waters around our metal here, that positive charge is going to be from our metal ion. And in this case, we have aluminum with 6 waters around it, so aluminum 3+. And what happens when we have metals with a very positive charge, meaning 3+ or greater, is that our water molecules that are bound to this metal actually become much more acidic. And so essentially what's happening, this high positive charge on our metal is going to pull the electron density from our oxygen, and that is also going to take away some electron density from our oxygen-hydrogen bond, basically make this bond a lot weaker. And so when it does that, another water can come in, assuming this is in solution. So if our metal ion is in solution, we have water come in. We actually deprotonate one of the bound waters, so we end up with a metal hydroxide at that point, and of course produce hydronium. And so this will actually cause the solutions, or the pH of our solutions rather, to be acidic. And so that is another example of how we can affect the pH of a solution. Beyond just adding an acid or a base, we can add a highly charged metal ion, and that will also have an effect. Okay? That's it for our pre-lecture. If you do have any questions, please let me know. Otherwise, I hope you have a good day, and I will see you soon.